Welcome back. Errors are an inevitable part of programming, but how we handle them defines the quality and reliability of our code. Today, we're diving into error handling in Python. By the end of this video, you'll understand how to manage errors with try, except, and finally, and even create your own custom exceptions for better error management. Let's get started. Errors in Python can be categorized into three main types. Syntax errors. These errors occur when your code doesn't follow Python's syntax rules. For example, forgetting to close quotation marks or misplacing a colon can lead to syntax errors. Here, we forgot to close the quotation marks, leading to a syntax error. Logic errors. Imagine you're writing code to divide 10 by 2, but you accidentally divide it by 5. Python won't throw an error because the code is syntactically correct, but the result isn't what you intended. This is a logical error. Your program runs fine, but the output isn't what you expected due to a mistake in your logic. In this case, the program outputs 2 instead of 5, but since there's no crash, the mistake might go unnoticed. Logical errors occur when your program runs without crashing, but the output is incorrect because the logic behind it is flawed. These errors are harder to detect because they don't stop the program or raise an obvious error. To catch logical errors, you usually need to rely on thorough testing or carefully reviewing your code to ensure it behaves as expected. Exceptions. These occur during runtime when Python encounters something unexpected, like dividing by 0. Here, Python encounters a zero division error at runtime because division by 0 is mathematically undefined. This type of error causes the program to crash unless handled. Understanding these errors is the first step towards writing more resilient code. Python provides a way to handle exceptions gracefully using try and except. Let's look at an example of catching a zero division error. As you can see, this produces an error. Let's dive deeper into how we can better handle this. Here's what happens. The code inside the try block is executed. If an exception occurs, the except block catches it, and you can handle it without crashing the program. By itself, this doesn't seem very useful, but it becomes more meaningful when used within a loop to simulate an interactive program. Let's look at this example. If we choose 0, you'll see that we get the zero division error and the program crashes. This is not very user-friendly, as the program should continue running. To handle this more gracefully, we can use try and except like this. Now, as you can see, the program doesn't crash anymore. It simply warns the user that they can't use 0. You can also handle multiple exceptions using multiple except blocks. For example, if we try to use a letter, the program will also crash. So let's add an exception to prevent that. This flexibility ensures that your program continues running even if an error occurs, giving your users a more seamless interaction. Sometimes you want to execute cleanup code no matter what happens. This is where the finally block comes in. It's executed after the try and except blocks, regardless of whether an exception was raised. This is particularly useful for cleanup tasks like closing files or releasing resources. Let's take a look at an example where we open a file, read from it, and make sure it gets closed no matter what. Here's what happens. In the try block, we try to open a file and print its content. If the file doesn't exist, the except block catches the file not found error and prints a message. Regardless of whether the exception occurred or not, the finally block executes. It's responsible for closing the file to ensure that the file resource is released properly, even if an error happened earlier. This is especially important in scenarios where failing to clean up resources, like closing a file or releasing a network connection, could lead to memory leaks or other issues in your program. As we know, we can use the with statement to avoid having to manually call close, but this example is just to make the concept easier to understand. In some cases, you might want to perform actions like logging, notifying the user, or sending a signal to another part of your application to let it know that an operation was completed. This is where finally helps keep your program running smoothly. Python allows you to create your own exceptions, making error management more specific and tailored to your application. To understand custom exceptions, let's first take a quick look at what a class is. A class in Python is essentially a blueprint for creating objects. It defines the attributes, which can be thought of as the data or variables, and methods, which are the functions or actions that belong to those objects. So a class is like a mold from which multiple objects can be created, each with its own unique data and behavior. Now, let's move on to creating a custom exception by defining a class that inherits from the built-in exception class. In this example, customError is a new exception class that inherits from Python built-in exception class. The init method allows us to pass a custom message when the exception is raised. Now, let's see how we can use this custom exception in a program. Imagine you're checking if a number is valid, but it should be non-negative. If the number is negative, we'll raise our customError exception. In this code, we use raise to trigger our custom exception when the number is less than 0. Next, let's see how we can catch and handle this custom exception. Here, if the number is negative, the exception is caught in the except block and we print a customError message. Creating custom exceptions like this is a great way to make your error messages more descriptive and specific to the needs of your program. Instead of using general exceptions, you can give more meaningful feedback to users or developers. This approach also helps you see exceptions as tools for checking conditions in your program, allowing you to provide targeted responses based on whether those conditions are met. Now, I briefly introduced classes so that you don't feel lost with the concept. If you're not familiar with classes yet, don't worry. We'll be diving deeper into them, along with object-oriented programming, in upcoming videos. In the meantime, feel free to explore more about classes on your own. Let's bring everything together with a more realistic example. Imagine you're building a program that processes a file where users upload their contact information, but you need to ensure the file exists and its content is valid. First, we'll create a custom exception to handle missing or invalid data in the file. Then, we'll validate that the file exists, can be read, and contains the correct data format. Once the file passes the existence and format validation checks, the program proceeds to process its content. Each line of the file is split into 3 components: name, email, and phone. After ensuring the format is correct, these components are then printed to simulate further processing, demonstrating how exceptions allow the program to focus on valid data without worrying about errors. To ensure the program remains user-friendly and resilient, the main execution is wrapped in a try block. Specific exceptions like file not found error and invalid data error are caught and their messages are displayed directly to the user, providing clear guidance on what went wrong. A generic except block is also included as a safety net to catch any unforeseen errors, ensuring the program doesn't crash unexpectedly. Finally, the program allows users to gracefully exit by typing exit at any prompt. When this happens, a friendly message is displayed to thank the user and close the program. This structure ensures the program continues running even when errors occur, maintaining a smooth and positive experience while showcasing the full power of exception handling. This example demonstrates how custom exceptions help make error handling more descriptive and tailored to the specific needs of your program. By raising these custom exceptions, we make sure the program behaves predictably, even when there are file-related issues or malformed data. Today, we cover the fundamentals of error handling in Python, how to identify different types of errors, use try and except to catch exceptions, used finally for cleanup, and created custom exceptions to make error management more tailored to your needs. These techniques will make your programs more robust, reliable, and user-friendly. Now it's your turn to put what you've learned into practice. Try building a program with your own custom exceptions, or experiment with try and finally to see how they work together. The more you practice, the more comfortable you'll become with managing errors and building better programs. If you enjoyed this video, don't forget to like, subscribe, and drop a comment below. And in the next episode, we'll dive into testing your code. Trust me, you don't want to miss it. Happy coding, and I'll see you in the next dimension.